Hello, and welcome to this video lesson on data types and structures, computer fundamentals for Full Stack Academy of Code. We have a couple quick demos here just for kind of fun and to give you a preview of what's to come. If you've worked with floating point math before, you may know that 0.1 plus 0.2 surprisingly does not equal 0.3, it equals 0.3 and a whole bunch of zeros and 4. Maybe not what you were expecting. If I have an array of strings such as data and full stack lecture and structures, and we call the native JavaScript sort function here, then you might expect, well, DFLS, it looks like it's pretty much already alphabetical, and yet what we see is that it sorts capitals first. So that's interesting. Wonder why that could be the case. Another example here is we put some numbers into the sort, and instead of sorting numerically, as you might expect, we get this alternative order, 1701, 1920, etc. Another very fun one, I think, if I can grab it here. So what is the length of 2 beers? Well, you might be unsurprised or surprised to discover that it is 2. Famously, not a number, nan, does not equal itself. And even more famously, what is the type of not a number? Well, not a number is clearly a number. So these are all fun, and there are actually good reasons for every one of them, and we're going to explore that as we continue with this lesson. Okay, so it's not quite as simple as the files are in the computer, but we're going to see some details as we go along. There's a lot of reasons to cover this material. We want to demystify foundations. The way that the computer works as a physical piece of machinery informs and influences how we design software for it. The limitations of the machine in terms of how it accesses and moves around information end up having non-trivial effects on the shape of our algorithms and the way that those solutions work. Now, there's been a ton of research in this material for decades, and we want to be able to draw on that research when appropriate. That doesn't mean that we have to be dictionaries of every existing algorithm out there, but being able to talk about this information, being able to discuss it with other developers, sharing that common language is going to be an important part of being an effective software designer. And there's also a practical aspect of being able to interview well in the interview circuit here. That's not the highest priority reason we would do this, but it is something to take into consideration. So a lot of information coming up. Let's start with some abstract ideas. This is not a broken video. You're looking at a blank slide. And the question I would have for you is this slide communicating anything? Some of you might say, perhaps it's communicating the color black. Black as a concept only really makes sense in contrast with something else, right? If the entire universe was black, so to speak, then there would be no concept of light or red or something else. So information in information theory is actually defined as a sequence of symbols, where symbols are things that we can differentiate among, and we can also ascribe our own meanings to them. So differentiation, this versus that. On a philosophical sense, a lot of what former thinkers in this field were trying to grapple with was the notion of truth. Philosophy is often concerned with what is real, what is not real, what is logical, what isn't logical, etc. And up until about the mid-19th century, the primary means that people had to discuss this were rhetorical in nature. If it sounded good, it was convincing. George Boole wanted something a little bit more formalized in order to be able to encode statements, predicates, about whether or not things were true, and then perform operations on those predicates and say something like true and false is, well, false, or true or false is true. So he developed a formal notation to be able to write this stuff down, where 1 was true, 0 was false. A negation sign indicated the opposite, so not true and not false. And things like Boolean conjunction and Boolean disjunction, which we know of very commonly as the and or operators. Another way of representing this is with so-called truth tables, where for every given set of inputs, X and Y are both statements which might be true or false, we see what the result of a given operation, like the AND operation, is. So on our left chart there, we can see that X and Y is only ever true, or 1, if both X and Y are themselves true, are noted as 1. Another way to show this is with these diagrams, which are known as logic gates, which graphically give the idea of X and Y being inputs to some arbitrary machine that creates outputs. And or, and not will be distinguished according to the shape here. So we can imagine that if we had a machine that spit out results according to these truth tables, this is a way we could label them graphically. From these axiomatic nuggets of I'm just going to assume that there's something called true and there's something called false, and that the opposite of false is true, and so on and so forth. If we follow the rules of Boolean logic, we start to discover a lot more interesting combinations of rules. One of the most well-known, third from the bottom here, is De Morgan's law. It's actually a pair of laws, left and right. And De Morgan's law, as an example, states not A and B is equal to not A or not B. In other words, if we have two statements and both of them are true, the opposite of that is either one of them is false or the other is false or both are false. It makes logical sense, but the lovely thing about this is since it's an algebraic notation, it's a bunch of symbols we can move around on a page, and if we follow the proper rules, we can discover conclusions that always hold within the system if the system is consistent. In the 1930s, American mathematician and electrical engineer Claude Shannon, otherwise known as the father of information theory, was realizing that Boolean algebra could actually be processed not just by a human with pencil and paper, but by judicious wiring up of switches. So he called it switching algebra. And in switching algebra, a 1 or true is actually encoded as a state, a physical state of machinery, specifically an on state. And a 0 or false is encoded as an off state. Now, these don't have to be electrical switches. I've seen logic gates built out of Lego. I've seen logic gates built out of hydraulic switches. Anything where a switch can direct flow or energy from one area to another, you can create this kind of situation where it actually ends up modeling and processing Boolean logic. Side note, Claude Shannon was well known as a bit of an eccentric with many skills and talents, including juggling. So here's an example. We got this kind of abstract version of a logic gate here, and we can imagine that this is part of an electrical circuit. So electrons want to flow through the wire from left to right. We've got an application of a voltage. And we have two switches here, both in the open or off position. So that's kind of like we have two statements which are both currently false. And we can see that the result of both of those things together is also off or false. No current can flow through this system. If both of the switches were closed in the on position, then current could flow through and our result would also be on. So the only time we have an output of 1 or on or true is if both of the inputs are closed or 1 or on or true. So in this way, we're modeling an AND gate. We're saying that the left and right predicates are both true only if both of them are true. Well, you shouldn't be surprised that if that's an AND gate, this set of switches wired in parallel models an OR gate. We could say that the output is only true or on if either of the switches or both are closed or on or true. And these are just two examples, but there's many versions of these with AND and NAND and NOR and not AND, which is NAND and things like that. So the idea of processing things logically or computing things, coming up with results according to rules using a machine was not a new one. One of the earlier successful designs was developed in the 19th century by a gentleman named Charles Babbage. And Charles Babbage created a difference engine and an analytical engine, at least on paper. His assistant, Ada the Countess of Lovelace, otherwise known as simply Ada Lovelace, was responsible for helping to transcribe and publish and send his notes as letters to various international colleagues. And in the footnotes for some of these, Ada Lovelace wrote examples of how the difference engine could be used to calculate certain programs, such as calculating an algorithm that shows numbers of Bernoulli numbers. These footnotes showing how to use the machine and code it and program it and move the elements of the machine into the correct position to calculate these algorithmic or stepwise calculations are pretty much considered to be the earliest examples of computer programming. And Ada Lovelace is often cited as the first computer programmer, which is quite a feat since there were no computers yet. The difference engine, the analytical engine, are specialty machines. They're not general purpose computers. They can't do everything that's computable. They can compute a subset of problems, mostly math problems of a specific structure. And you can see that they're very large and ungainly and have a lot of cogs and gears, elegant in this kind of steampunk way. But the problem, of course, is these large, heavy machines have big moving parts, and they're slow. I mean, we got to hand crank this thing and wait for it to produce a result on the other end. So it's hard to build a system with all these mechanical switches. What is a good alternative? It turns out electricity is a great medium for this. It's a remarkably useful medium. Signal propagation, the moving of our information around in the system, is very fast. Electrons flow in a current through a metal wire at around 1/3 to 99% the speed of light. Or there's a difference between the flow of the electrons and how fast they go versus how quickly the signal of the electron current kind of moving through the system is. But in any case, it's very fast. Electrons are very small. It's 10 to the negative 15 meters, or about 5 femtometers. So you can fit a ton of them in a small space. And that means they can have a lot of different information whizzing around in a very small area. And finally, if we're encoding all of our information in the form of electricity moving around and processing logic that way, it's very helpful that the electricity, if it comes out of the pipe on one end, is able to be wired up to devices such as light bulbs or things like that, and trigger them, make them do something in the physical universe that we can observe as humans. So our signal becomes our action, and that's a very handy feature. One of the earliest ways we could do this was with mechanical switches called relays, which are basically electromagnets, where we'd have switches that could turn on and off based on other electrical signals. Those are problematic because they're large and clanky and big, and it's a bunch of magnets. Another alternative are these smaller things called vacuum tubes. And vacuum tubes, they have the advantage of no moving parts, no mechanical failure, in the sense that there's something that's sticky or needs, lubrication or something. But these vacuum tubes, they're problematic in their own way. They get very hot. They fail after a while. They're temperamental. Some of them have different voltages. The way that they work is electricity could flow. Electrons can jump from the anode to the cathode, meaning conventional current goes from the cathode to the anode, only if this heating element is active. So it's an electrical switch. Current can be switched on or off going through the system based on this other part of the system that's also activated by electricity. So you have an electrical switch which is not physically turned on and off by a hand flipping a switch. It's turned on and off by some other current being active. So you get electrical switches being turned on and off by other electricity. This is an example of the Colossus computer from 1944. It had 2,400 of these vacuum tubes. They're kind of big, they're warm, they're constantly breaking. It can be done, but it's kind of a pain, mechanically speaking. The next step up from a vacuum tube as an electrical switch is the transistor, or solid state electrical switch. In a transistor, you've got current that comes from a source terminal, and it's going to flow through a gate terminal into a drain terminal. So that's that S, G, and D there. And the gate acts like a bridge here. So current can flow through it, but only when the gate is active. And the thing that activates the gate is the application of a voltage or electricity to it. So again, we have electrical switches being triggered by other bits of electricity. The silicon germanium transistor we just saw was a reproduction from the one from Bell Labs. But now we've miniaturized these as far as they can pretty much possibly go. This is an example MOSFET, metal oxide semiconducting field effect transistor. And just for some perspective here, each of those white fins, so to speak, is only 22 nanometers thick. Nanometers 10 to the negative 9 meters, a billionth of a meter. So just to give you a sense, a virus is about 20 to 400 nanometers. These things are smaller than viruses. We make them with photolithography. It's a very amazing technology. We can't really make them smaller. We actually have the technology to make them smaller, but then they won't work. And the reason they won't work is because of quantum mechanics. At the super duper small scale, physics starts to break down and become a completely different system from classical mechanics. So electrons can teleport from place to place, and the system no longer behaves reliably in the way we would expect in a sort of intuistic human sense. So how does this work? Current wants to go from a source terminal and drain into a drain terminal. And along the way, it has to pass through a gate terminal. And this gate can be activated by the application of voltage or electricity. Just like we saw in the previous example, this is a tiny electrical switch. Let's diagram these with these green bubbles here, if you're red-green colorblind, I apologize. I tried to shift the tone a little bit so it would show up better. But each one of those transistors labeled in those circles is this idea of this tiny little MOSFET where current could pass through it if the gate is active. Well, that's just a switch. So if we wire up two switches in series, it's exactly that AND gate we saw before. Supply current will flow through the transistors to the output if both transistors, and only both transistors, not one or the other, are on. Conversely, we have an OR gate on the right, which is wired up in parallel. And if either transistor or both transistors are activated, current can flow through from the supply side to the drain side or the output side. So again, we've got electrical switches that are being wired up to other electrical switches, and we can start to do some fancy stuff here. And usually in diagrammatic format, we will show these in a simplified kind of iconographic way. Well, what kind of stuff can we do with this? Here's an example. This is called a full adder. It takes in two bits, two ones or zeros. So B and A over there are our bits. Each of them could be a 1 or a 0. And it adds them together. So this is a machine that can add 1 plus 1, or 1 plus 0, or 0 plus 1, or 0 plus 0. You know, there's another input called C that stands for carry. And the idea is that if this is wired up to some other calculations, maybe there's a bit left over from adding 1 to 1 and getting 2. And on the right, we can see that there's a sum and carry bit that are coming on the output. And based on our inputs, if A is 1 and B is 0, then the carry is 0 as well. The carry output on the right will be 0, and the sum output on the right will be 1. In other words, adding 1 to 0 gets 1. Wow, amazing stuff. Adding 0 to 1 will get the same result. Adding 0 and 0, both of the bits on the right will be 0. If we put in an A is 1 and B is 1 on the left and carry is 0, well, the binary representation is going to be 1, 0. So that becomes a carry of 1 and a sum of 0. So we need at least 2 output bits to show the proper result of this kind of thing. Now, we're not going to actually go through and verify all the logic here, but you can imagine with these switches that can perform very minimal logic like AND and OR, we would say something like, if B is on and A is on, then the sum should not be on and the carry should be on. So just wiring up these logic gates together correctly gives us machines that can now add 1 and 1. And adding up more of them, we can start to add multiple digits together. And we can add multiple numbers. And if we do even more wiring, we can start doing multiplication and division and all sorts of clever things. And once we've got a lot of math going on, if we just store that information in places, we can use it as the input for other calculations, and we start to develop up something complicated enough to do general calculation. So who figures this out? Who figures out that if we just do the right calculations in the right sequence with primitive operations, we can calculate anything? And how do we really know that that's the case? It turns out at the turn of the century, this is the 1900s we're talking about, early 1900s, late 1800s, many mathematicians were working together to figure out what is the one true system of mathematics. It turns out that there's many different fields in math, and they don't all proceed from the same axioms. Yet, if you go far enough in any given field in math, you often start looping around and discovering other fields of math or being able to simulate other fields of math. So people wanted to know, okay, what is the one true set of axioms that if I just chose the right rules from the beginning, I could go prove all the rest of mathematics? Unfortunately, it turns out this is not possible. Kurt Gödel, famously with his incompleteness theorems, showed that any such pursuit is doomed to fail for reasons we won't go into great detail. But two of the people who were really involved in this process were Alonzo Church and Alan Turing. Alonzo Church in Princeton was developing a symbol manipulation language called lambda calculus. And Alan Turing, showed on this slide, in England was developing something called a Turing machine. It turns out both of these are important, and both of them are actually identical in what they can compute. They are equivalent logical frameworks. But we're going to focus on Turing machines. A Turing machine is the idea that you have an infinite piece of hypothetical tape that contains cells. And at any given moment, you can either move to the left or right and view a different cell, or you can read what's currently in a cell or write something to the cell. And you've got some sort of if-else logic that says, if there's something in the cell, write to this or go right or do this. And this symbol rewriting framework is able to actually calculate anything calculable. It seems impossible. It's really amazing that from such simplicity, you can actually generate any kind of computation. But the essence of it is that as the machine is reading and writing, it can use that information to say what to do next. If I see a 1 here, go 2 spaces left. And if I see a 1 there, go 2 spaces right, or something like that. So from this, we can simulate all sorts of devices and machines. And people got really excited by this because after Alan Turing proved that this could compute anything computable, people started thinking, well, wait a second. This is a general purpose computation engine. If a hypothetical machine can do this, maybe we can make real machines that do this. John von Neumann, another mathematician, invented the ENIAC computer in 1946, one of the first electronic programmable computers. It was designed to do calculations for the H-bomb, part of the Manhattan Project. A newspaper at the time described it as a giant brain, weighed 30 tons, cost $6.8 million, and it had all of 0.1 megahertz of speed. His design for this computer basically boils down to what we call now the von Neumann architecture, where we have a central processing unit that can do math using an arithmetic logic unit. It can read and write information to some memory, kind of like that infinite tape from the Turing machine. And it reads in from an input device and sends information to some output device. Maybe the input device is a keyboard. Maybe the output device is a sequence of lights. Who knows? Or a bunch of buttons to some sort of speaker or something. This architecture is basically what now underpins almost all modern personal computers. And it is very influential in terms of how we now have to write our programs. So in the memory will be stored all these ones and zeros, these bits, these true false values, these on-off states. And our bunch of switches, the CPU, all wired up correctly, will somehow magically, not actually magically, of course, do the proper calculations based on input. So what ones and zeros do we put in the memory, and how do they get there? And why does this have such a huge impact on the way we write programs? For that, we're going to talk about data storage. Again, we're in the 19th century with late 1800s, 1880. And in the 1880s, the US Census was taking 8 years to perform. This is a problem because the US Census constitutionally must be performed every 8 years. And the country was only getting bigger population-wise. So people needed to find a solution, and they needed to find it fast, lest there be a political catastrophe. This gentleman, Herman Hollerith, graduated City College of New York, Columbia, and MIT. His doctoral thesis was called An Electric Tabulating System in 1889, and it proposed a certain kind of data storage plus electrical signals to count results. The thing that he used, which he's holding in his hand right there, were punch cards, which he didn't invent. He took it from Jacquard looms. But these punch cards were a compact way of indicating data as a sequence of holes in a piece of paper. Punched in the right way and fed into Hollerith's tabulating machine, we can see these dials up here. A bunch of wires would brush over the holes, contact a pool of liquid mercury underneath, close an electrical circuit, and cause each of those dials in the proper locations to tick up. And that tick would register, oh, somebody is a woman or a man, or they have kids, or they don't have kids, or they are a carpenter or a doctor or something. So this machine was super successful. The 1890 census took only 1 year and came in under budget. Tremendous success. His punch cards led to not only the success in the census, but his company, the Tabulating Machine Company. It merged with several others to become the Computing Tabulating Recording Company. And that company was renamed in 1924 to International Business Machines Corporation, otherwise known as IBM. Fast forward, this is NASA 1957, technically not NASA, but kind of a satellite office of a government space agency that was then folded into NASA. And this is an IBM computer. It's an IBM 704 computer. And guess what it's using? It's using punch cards. In fact, the operator, the programmer here in the foreground is feeding punch cards into the computer running a program. Now, by the 50s, punch cards were already on their way out. They're problematic. They're problematic for a couple of reasons. They're paper, so they're easy to damage or destroy. You have to keep them all in order. You got to keep numbering them, make sure that they're correct. They're easy to get out of order. They're easy to lose. They're easy to not, mark down what you're doing. And they're difficult to edit. Once you've punched a hole, you can't really easily unpunch the hole. So we need something that's denser, has more information, it's more foolproof, it's more machine-based, less human-based. And that turns out to be magnetic storage. So this is magnetic tape storage. Magnets, as we know, has a positive and negative polarity. And on this piece of tape, we've got an electromagnetic read-write head that would magnetize sections of the tape with either one polarity or the other, positive or negative. And then later it could read back that polarity and tell you what sequence of positives or negatives were recorded on the tape. This, by the way, is United States Navy, not Admiral, Rear Admiral, excuse me. United States Navy Rear Admiral Grace Murray Hopper, 1906 to 1992, graduate of Vassar and Yale. And she was working with the UNIVAC tape storage. She has a number of claims to fame. One of the silly stories that is true, but it's not very important, is that she helped popularize the name bug. It's actually really amazing. There's her notebook preserved with a moth taped inside it saying first actual example of a real computer bug, which they found in the system and debugged. Much more important, Grace Murray Hopper developed compilers. And we're going to talk about compilers later in this presentation. But this was a tremendous leap forward for how programs are written and what programs are capable of doing. Now, tape storage is still used today. Magnetic tape storage is cheap and it's large. So this is a government archive system, the NERSC, National Energy Research Scientific Computing Center system, in use since 1998. It's still the most cost and space efficient massive storage strategy, for example, for data centers and backups and things like that. But some downsides, it's very slow. You've got a moving magnetic piece of tape and it's in a sort of scroll format. Once upon a time in antiquity, important documents were recorded in scrolls, and they offer only sequential access. You need to scroll to a certain point. So remember rewinding and fast forwarding VHS or audio cassettes, it's the same idea. Tape drives are essentially scrolls. If I wanted to copy something from the beginning to the end of the scroll, and I had limited space here, I would have to basically look at the beginning, scroll to the end, scroll back to the beginning, scroll back to the end, so on and so forth. It's difficult to go directly to a particular place in the scroll. Conversely, from roughly the 100s through the 300s AD, the scroll was gradually replaced by the codex. A codex is a handwritten book. This is an example of a printed book. Specifically, it's a Gutenberg Bible. Not that that's important to anything we're talking about. But the scroll was gradually replaced. And some of the advantages of the codex include you could write on both sides of the paper, and also random access. If you put your thumbnail on roughly 3/4 of the way through the book, and then you flip open to it, you can go straight to that point. You don't have to go page by page by page. So magnetic tape drive storage was like the scroll of the computer era. We needed something that was more like the book of the computer era. It could hold more information in a smaller area, and we could easily jump straight to any part of that information. Enter the hard disk drive. In a hard disk drive, or HDD, invented in the 50s but became really common by the late 80s. There are solid platters, a little bit like an LP or record. And these things spin very fast, about 5,000 to 10,000 revolutions per minute. And then on the end of a read-write head, there is a electromagnetic read-write head on an arm, and that arm can go float over the spindle, over the disk, directly to a particular track. And these tracks are basically concentric rings. So if I wanted to copy back and forth between two parts of the track, well, I would just spool the disk, spin it up, get the read-write head to go over the track I wanted, read some information, go back over into maybe more toward the center of the disk, dump the information, go back and forth, et cetera, et cetera. I wouldn't have to read or travel through all the other concentric rings in the meantime. I could basically skip over just like dropping a needle onto a record. Take out the disk from the hard disk drive and put it in a piece of plastic, and it's a floppy disk. And the idea here is you don't have all the machinery that actually knows how to read and write to the disk that still lives inside of some kind of drive carrier. But now you can take the disk out and you can move it somewhere else, and you've got portable media in which to record information. Other versions of portable media include compact disks, or CD-ROMs, compact disk read-only memory. And this is an optical drive format. Instead of magnetic polarity, which can degrade over time or get messed up by speakers and other things, we have divots laser engraved in a surface that reflect or don't reflect, as the case may be. And a laser can then go bounce off of this and detect whether there's a pit or a land, it's called, and read in bits that way. A little bit of trivia. It's not that the surface is a 1 and the pits are a 0 or vice versa. It's actually changing from a pit to a land or a land to a pit is a 1, and not changing for any given amount of time is a sequence of zeros. So downside, it's very difficult to change physical hulls. It's very difficult to change these laser engraved things. This is read-only memory. Rewritable technology came later, but it's tricky. And with magnetic tape, well, you can change it, but it's a little slow. It's a moving system, and the tape, it can degrade over time. So flash forward and we start to just say, look, we know clever ways of wiring up logic gates so that they can store information temporarily, basically with like electrons just in a loop, a bunch of charge just stuck somewhere. And we can read and write that charge. Now that system only works as long as the entire logic gate system is being fed power. So this is known as volatile memory. But we're going to see in a moment a way that we can make this a little bit more persistent. So this is called flash memory. Flash memory is just wiring up a bunch of electrical switches, as a bunch of transistors in a clever pattern that lets us store charge temporarily. They were popular for things like camera storage cards and USB sticks and stuff like that. But it's only recently that persistent flash memory that doesn't go away when you turn it off, has become affordable and large enough for computer drives. One way that we can make this persistent is with what's called a floating gate transistor. So you'll recall that in a transistor, current will flow from the source to the drain through a gate. And that gate can be switched on and off by application of electricity. But a floating gate transistor is slightly different. In a floating gate, there's two gates. There's the control gate, which switches the system on and off. But there's also a floating gate, which holds charge. So that's a way of storing information, which we can read later. And the beautiful thing of a floating gate is even if power is not currently running through the system, the gate will capture that charge and hold on to it for future checking. So solid state drives have no moving parts. They're just microcircuitry. And they're shock resistant, faster than hard drives with moving parts. They don't degrade due to magnetic issues so much. They do slowly leak over time. The charge gradually dissipates, but we're talking about an order of a couple of years without power. Some downsides still, things like poor read-write longevity, complex controller firmware, expense, etc. But we're going to view some of those trade-offs in a moment. So everything we've been talking about is a place to put these ones and zeros, this information that we're going to operate on and do calculations with. And we tend to call that stuff storage. It's big, we have a lot of it, it's cheap, but it's not very convenient to actually use. We don't actually do calculations on a hard drive. The hard drive is slow. What we would like is to have the information closer to the brain, closer to our fingertips. And for that, we have something called memory. And the distinction between storage and memory is based on a few things, but it's all just technology for holding information. And we're going to see some of those dividing lines. So the metaphor here is storage is like a filing cabinet. It's big, it's slow, it's far away. Memory is more like a desk. It's close, it's fast, it's small, but it's also ephemeral. It's not very secure. The information could be lost easily. This is a stick of DRAM, dynamic random access memory, and it's our first example of memory as opposed to storage. It stores bits in tiny capacitors. It's leaky. If this system stops receiving power at any given moment, all of those charges will dissipate and go away very, very quickly. So it's not persistent like SSDs, solid-state drives are, but it is much faster than an SSD because we don't have to capture that charge in a floating gate, which slows down the system a little bit. Even closer to the metal meaning the CPU, the chip, the processing power here. On the chip itself, there is space for memory. And this memory is in the form of tiny transistors, not capacitors or floating gate transistors. So a huge portion of this chip is just a shared cache of memory that's very fast. And then another portion of this chip is a smaller area that's much, much faster. Then another portion is an even smaller area that's very, very, very fast indeed. And then even smaller than this, not marked down at any given moment, are little buckets called registers. And the registers are the absolute endpoint when it comes to memory. Basically, all of the processes, all of the operations, all of the calculations that your computer chip is doing happen with registers. Load one number into register A, load another number into register B. You can add the two together and put the result in register C. So all of the actual operations are being carried out on registers, which are parts of the computer chip that can hold information. And those registers are small. They can only hold, say, 32 ones and zeros or 64 ones and zeros. It depends what kind of system you use. Because a register is so fundamentally important to the architecture of a computer chip, the size of the register, the number of ones and zeros or bits that it can hold, is known as the word size of that computer architecture. So you would say a 64-bit word. In other words, the largest chunk of information that your computer is actually capable of dealing with at a time. Now, there's a huge trade-off here. Registers are tiny. They can't hold a lot of information. They're just very, very, very fast. They're also very, 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 very expensive because they're all those micro-controlled circuitry, tiny little transistors that we saw earlier. whereas something like a big old magnetic disk is just a big chunk of space. And you can have a piece of machinery that adds, magnetic polarity one way or another in big giant chunks, kind of much more coarse. So a disk tends to be much cheaper, but also far larger. Just physically speaking, you can hold way more information. And this kind of trade-off between size and speed and expense is one of the important trade-offs here. Another important trade-off is volatility. So remember that there's a difference between storage and memory. And one of the distinguishing factors is if I turn off the system, if I power down the computer, does the information persist or does it go away? Here, there's a dividing line halfway down the table, and below that dividing line, solid state, hard disk, optical, that's persistent storage. Even if the system is off, the information is preserved. Everything above that dividing line is faster, way, way faster. Check it out, 100,000 nanoseconds access time for SSD versus only 70 nanoseconds of access time for RAM. However, if I turn off the computer or lose power, all that information will dissipate immediately and it'll be gone forever. This is the distinction between saving your work or not. Now, why do we need things like L1 cache, L2 cache, RAM? Basically, there's only so many registers in a computer, and they're small. They're as fast as the computer is. The computer does operations on the registers, so they are where the buck stops. And every time the computer does a bunch of operations, we call that a cycle. So accessing a CPU register happens on the order of one cycle. Every cycle, I can access registers, perform some math, and put the result in other registers. But since the registers are so small, it would be really a huge drag if we had to wait for all the information to come from the drive, from an SSD or hard disk. That would take forever. We would constantly be loading only a tiny bit of data from the drive, doing some operations, putting a tiny bit of data back in the drive, waiting for it to come back, and so on and so forth. What we need is a way to pull more of the information as close to the CPU as possible. So we have caches, which are very, very fast, but still pretty small, and higher level caches, which are very fast and getting a bit bigger, 256,000 bytes. And then we have RAM, and RAM is the sweet spot. RAM is both big and fast. It's not persistent, so that's a downside. But in terms of making a computer work well, RAM is great. Because look at how fast it is. We can get information from the RAM in only about 70 nanoseconds, but we can hold 8 billion bytes, 8 gigabytes in that RAM. Really nice. This is why if your computer is slowed down because it's trying to run a lot of programs simultaneously, one of the best ways of upgrading it is making sure you have enough RAM. But as we can see, RAM is only one part of the puzzle. Now, it can be difficult to humanly understand all these numbers. It's like, okay, 1 billion bytes, 1 trillion bytes, what is that? 60 billion nanoseconds, 100,000 nanoseconds. Here's the exact same information scaled up to real world numbers. And these are accurate numbers. These are not arbitrarily chosen. So if we said a clock cycle, instead of taking place a billionth of a second, took place every second, and if 1 byte corresponded to 1 milliliter of volume, a milliliter is a cubic centimeter. It's a small amount of liquid. This is what we would end up with. A register would be like a teaspoon, and accessing it would take about a second. A cache would be like 17 gallons, and it would only take 2 seconds to access. So you can see that it's really nice to have these caches so that we're not constantly fetching teaspoons from, a swimming pool or something downstairs. RAM is like that multiple Olympic-sized swimming pools that's downstairs. It doesn't take very long to go get information from RAM, and we can hold a lot in RAM. But compared that to something like the Hindenburg in another city, you could see, yeah, well, the Hindenburg is huge, but we'd have to go all the way off into some other city to go get it. And going to something like a tape drive, from the computer's perspective, that's as if it would take 2,000 years to go fetch that information from the tape. But the size of that is gigantic. Chagan Lake, if you don't know, is from nuclear testing. It's basically a giant nuclear, cave filled with water. So we have a sense now that there's a physical trade-off with all of these layers. And if we have a system that's composed of multiple layers, we get some of the benefits of all of them. We can store a lot of information in the persistent storage. We can load it all up into RAM and caches to make it easily available. And our CPU can do operations on that information using the registers, which are part of the CPU. Now that we know where the ones and zeros live and how those different technologies compare in terms of cost and speed and size, what are we actually storing with our ones and zeros, with our on-off physical states? That's where we get into representations. Representations are all about, here's our ingredients. This is what we have to work with. How can we now encode or represent or model other ideas using just these ingredients? Well, we know we can model 1 and 0. We've been talking about it the whole time. If we say it's on, that's a 1, and if it's off, it's a 0. Okay, if we all agree that that's a rule, we can play by those rules and say, now I know what was a 1 and what it's a 0. But we probably want to have other numbers as well, right? So what about all of the integers, the whole numbers, from 0 to 255 inclusive? How can I represent 13 just using zeros and ones? How can I represent 28? How can I represent 64? It turns out if we use a positional notation system, we can do this. So we already do this with decimal. In decimal, if I'm starting to count up, I start to say, okay, I've got 10 ingredients to work with. 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. Those are all my ingredients. That's all I've got in the decimal number system. So if I'm counting up from 0 to 9, and now I want to count to the next number, what do? I don't have a symbol in decimal for the number 10. There is no symbol for the number 10. However, I can take my 1, I can start over from scratch. I can take my 1 and I can put it one place over and then start my count again. 1 and 0, 1 and 1, 1 and 2, 1 and 3, 1 and 4, 5, 6, 7, 8, 9. I get to 1 and 9. Where do I go from here? There's no symbol for 20. But that's okay. I can take up my second place value from a 1 to a 2 and start my count over again at 0. So the idea of a positional notation system is that the size of the number depends on where it is left versus right in this list of digits. So one place over is tens, the tens place. 1 10, 2 10, 3 tens. This gives me 10, 20, 30, etc. 2 spaces over is the hundreds place. 100, 200, 300. This is powers of 10. The thousands, the 10,000s, every time I'm multiplying by 10. I can do the same thing in binary. I'm going to count up from the start. 0. Okay, well, 0 is 0. 1. Good, I've got a symbol for 1. I want the next number. Uh-oh, there's no symbol for 2 in on-off. How do I represent this? I go one space over and I tick up to create 1 0. And that is my 2. Now I want a 3. Well, that's 1 1. Now I want one more level, 4. Uh-oh, I ran out of digits and spaces. I need to tick over again. 1 0 0. And I can keep doing this. And now my position is not multiplying by tens. It's multiplying by 2s. It's an order of magnitude for 2s. So I have a 2's place, a 4's place, an 8's, a 16's, a 32's, and so on and so forth. And through this positional notation system, I can represent, if I use 8 of these digit spaces, 8 of these cells, I can, it turns out, represent all of the numbers between 0 and 255 inclusive. Converting back and forth between decimal and binary is a bit of a pain. I have to go to every one of these cells, figure out what power of 2 it is, include that power of 2 or not, depending on whether the cell is on or off, and then I have to add up all the results to get my decimal conversion. Not very easy or intuitive necessarily. Well, this system is all well and dandy, but it doesn't seem to have everything we need. If I can represent everything from 0 to 255, how can I represent 1/2 or negative numbers? It's not clear from this. This representation won't suffice for things in between the integers, stuff like the real numbers. For that, we've agreed upon a bunch of rules. These are arbitrarily chosen rules. We could have agreed upon different rules, but these rules are very useful because they let us do a bunch of different things. And this rule set is from the specification called IEEE 754. IEEE 754 defines floating point signed doubles. What does that mean? This is going to come up in articles. People are going to say, oh, use a float, use a double, use a single. So what does this mean? First, let's tackle the sign bit. We use 64 of these bits to represent a number. And the first one is a sign bit, which represents whether we're talking about a positive number or a negative number. This, by the way, is why JavaScript and other programming languages actually have separate values for positive 0 and negative 0, because the rest of the bits will read as 0, but the sign might be on or off. And if it's on, it's a negative number, and it's off, it's a positive number. So that's why we have a notion of positive and negative 0. Now, why 64 bits? Well, remember back to the idea of computer architecture. In computer architecture, you've got these registers, and the registers are where we do the actual math. And the registers can only hold so much information. They're these small buckets. So maybe they hold 32 bits, 32 ones and zeros. That's the word size for that architecture. And if that's the size of our registers, it makes sense to have number values that use all 32 bits. For a while, that was the norm in computer hardware for consumer computers in the 90s and early 2000s. Nowadays, it's become very popular and successful to have 64-bit architecture. So our registers are a little bit bigger. That might slow them down slightly because now everything isn't as close together as it could be, but it lets them hold larger values. So a signed double value is 64 bits holding a given number. But not all of the bits are representing a number in the way that we saw with that binary representation a moment ago. Some of them have to say, well, how are you going to encode fractions? Let's think about this in decimal. If I want to encode half, 1/2 in fraction, I could do it using the slash sign. So I could have a numerator component and a denominator component. Another way I could do it is with a decimal point. I could say 0.5. In other words, a 5, where the 5 occurs to the right of the decimal point. If I move that decimal over, so it would be 5 point, in other words, 5.0, now it doesn't mean a half, now it means 5. And if I moved that point over again, so it's 50 point, now I'm talking about 50. So as I move a decimal point to the left or right, my number gets bigger or smaller. And if I move the decimal over to the left, it can even become fractional. It can become 0.5, which is 1/2, 0.05, 0.005, and so on and so forth. So floating the point lets us control whether there's a fraction or an integer or what we're dealing with here. In binary, we don't call it a decimal point, we call it a bicimal point, which is not a common word, and you won't really hear most people talking about it. But a floating point number has 11 bits, that green section to the left, where it says exponent, 11 bits, reserved for just saying where the point should go. And then the rest of it, those other 52 bits, are the fractional component that say what the number looks like. If it's a 34712, so is that 37.412? Is that 374.12? Is it something else? That's what the exponent portion is for. Now there's a bunch of special rules. There's encoding patterns for plus and minus 0, plus or minus infinity, and also, hey, look at that, not a number. Sometimes when I'm doing math, I end up with results that cannot be represented using this. They are not useful results, but they're still supposed to be a number. So we have an invented value in the number system called not a number, which is not really to say it's not a number, but it's more a number that we don't know what it is. We can't calculate it and represent it using the scheme, so it's a useless number, a non-usable number. That's why in JavaScript, type of nan is number. Makes sense now. By the way, this is also why when we try to do 0.1 plus 0.2, we end up with 0.300004. Decimal and binary and ternary and quaternary number systems like this, positional notation number systems can't represent all of the real numbers. There's a very good example of this in decimal. We can't encode 1/3 in decimal. What is 1/3 in decimal? It's 0.33333333333, 3 repeating on forever. It never stops. So we can't actually write that down. It's not representable using decimal. On the other hand, if we used a ternary, a base 3 number system, it would just be 0.1. 0.1 is 1/3 in base 3. So different bases allow us to represent numbers that some of the other bases can't. And guess what? If we try to do 0.1 in binary, that's not possible. It's actually 0.001001100110011, going on forever. So it cannot actually be shown in binary, which means when you try to do 0.1 plus 0.2 using floating point arithmetic, it gets rounded off. It gets rounded off because we've only used 64 bits to represent it, so the last bit is going to be off by a little bit. And then when we do the math and we convert it back into a decimal representation, that rounding error is still present, and we see something that's not the result we expected. Another format that we commonly use for numbers in JavaScript, or not just in JavaScript, but we use really for talking about numbers in computing, is hexadecimal. In hexadecimal, there are 16 symbols to use. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, C, D, E, F. A corresponds to decimal 10, B corresponds to decimal 11, and so on and so forth. So if I'm counting up in hexadecimal, I would say 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, C, D, E, F. And oops, I've run out of things to say. I have no more symbols. So now I move over one space and I start at 0 again, or 1 in this case. So I got 1, 0, 1, 1, 1, 2, 1, 3, 1, 4, 1, 5, 16, 17, 18, 19, 1A, 1B, 1C, 1D, 1E, 1F. And yet again, I've run out of symbols. So I tick up and I've got 2, 0, 2, 1, 2, 2, 2, 3, 2, 4, and 2A, 2B, 2C, 2D, etc. Why would we use a symbol number system that has 16 symbols in it? Well, really the reason is because everything in the computer is binary. It's all on-off states. But it's very difficult for humans to read binary numbers, to write them down properly without making mistakes, etc. But we saw also that converting between binary and decimal is not very natural or straightforward. You have to figure out what power of 2 every place corresponds to, use it or not, depending whether that cell is on or off, get all the components, add them together. It's a rough thing. And going from decimal to binary is much more tricky. There's an algorithm for it. So we want a way to easily talk about these binary numbers that's not decimal, that's easier to convert, and hexadecimal is that system because every hexadecimal symbol corresponds to 4 binary symbols. The hexadecimal notation 2 corresponds to the 4 binary digits 0, 0, 1, 0. The hexadecimal symbol A corresponds to the 4 binary digits 1, 0, 1, 0. And this makes it trivially easy to convert between binary and hex or hex and binary. If somebody tells me, oh, it's at memory address 5BD, I can tell you, oh, that's binary 0101 1011 1110 5BE. I said 5BE, right? I hope so. And if somebody tells me, oh, it's at memory address 1001 1000, I could say, ah, that's hexadecimal 98. And all I have to do is look at this table and go back and forth between the representations. Very convenient. So we have ways of representing numbers as binary and representing fractional values and negative values using IEEE 754 format. What about something like letters and text? Something more communicative. This was already solved with a binary code called Morse. Morse is a sequence of dots and dashes, long and short pulses, and every sequence of dots and dashes corresponds to a letter. We just assign letters arbitrarily. In Morse, they're almost arbitrary. They're actually biased so that the most common letters, like E in the English alphabet, are the shortest sequences. So letter E is a single dot. But it's more or less arbitrary. Well, we could just do completely random assignments, but it's helpful to have something that's easy to remember and look back to and check for errors. So why not just number all the letters from 1 through 26 or 52 if we're using capitals and lowercase? And in fact, we do something similar to that. One of the first formats for assigning letters to numbers is ASCII, the American Standard Code for Information Interchange in the 1960s. They're 7-bit unsigned integers. This means that they don't have a sign bit. They're not positive or negative. They don't have floating points, so they're not fractional. They're just numbers counting up from 0. And we put them in 8-bit spaces. Why? Because the computer word size, the architecture of the day, their word size for registers was 8 bits. But the ASCII code is only 7 bits. And that's because ASCII wasn't invented for computers. It was invented for something called the teletype machine. Well, once we started using it for computers, we just had this extra leftover sign bit, which people got up to all sorts of shenanigans with, using for different things like accents or other languages or whatever. So in ASCII, you'll note that the letter A starts at the 65th position, which seems arbitrary and strange, right? Why would we start A at number 65? Well, the reason is because we're not thinking decimally. We're actually thinking in terms of binary. Look where A is in binary. It's on the right side, the 4 digits 0001. And on the left, it's this group 100. So it is the first letter of the 100 series, discounting the 0th letter. Well, B is the second or 1/0th letter of the 100 series. C is the third letter of the 100 series. D is the fourth, and so on and so forth. It actually does count up from 1, 2, 3, 4. Just it's in a group which starts with 100. Why did they put stuff ahead of it? I don't know. You'd have to go ask them. This, by the way, is why JavaScript's native sort sorts capitals before lowercase. We wanted to have the capitals to be numbered as 1, 2, 3, as they are in binary, we can see here. But we also wanted the lowercase letters to be numbered as 1, 2, 3. If we intersperse them with capital A, capital B, lowercase b, then the capitals would proceed as 1, 3, 5, and the lowercase letters would proceed as 2, 4, 6. And that would be maybe a little bit trickier to work with. So the capitals come first and then the lowercase numbers and letters, excuse me. And that's why our JavaScript native sort sorts lexicographically in this format. Now, the problem with ASCII is we can only code 128 characters if we use 7 bits. And even if we use all 8 bits of a typical word size of the day, that can only be 256 different characters. In the standard character set for Japanese newspapers of the modern era, you have to know at least 2,000 characters. So clearly ASCII will not suffice for all human language. To ameliorate this, people invented Unicode, which is just a dictionary of all possible things that we might want to write down as symbols. There's 1.1 million spaces possible in the Unicode dictionary. Only 260,000 of them have been assigned. And each one of those assignments is called a code point in Unicode. Now, Unicode is not a technology. It doesn't talk about what format these things are stored in. It's just a numbering of symbols. So we say like 1 is A, 2 is B, 3 is C, so on and so forth. And the letter E with an accent is this, and etc. Now, how do we represent all of these Unicode values? One way is with an encoding scheme called UTF-8. UTF-8 is great because it's a superset of ASCII, making it backwards compatible. The letter I, which is Unicode code point hex 49, not decimal 49, hex 49. That letter I is the binary on-off states of 0100, 1001. Guess what? Even though that's UTF-8 encoding, it's also the identical encoding for ASCII. So if I was reading in an ASCII file using a parser, a program that assumes it's UTF-8 instead, I would see all of the correct letters because we use the same values. And if I wrote a UTF-8 file only using simple letters like A and B and C and 1 and 2 and 3, then I would end up with a file which an ASCII program could read in and it would look fine. But what about if I do something outside of ASCII, like the heart symbol? You'll notice this is a very high Unicode code point, not extremely high, but high. It's Unicode hex 2764. So that's the 2764th in hex, which is probably like, I don't know, 3,500 or something like that, value of Unicode. That is actually represented not as a single byte, but as 3 bytes in a row. This is a very clever encoding scheme. It is a variable width encoding scheme. Every symbol of Unicode will be assigned anywhere from 1 to 4 different bytes to actually make up that symbolism. These things are called code units. And the rules for this are not super germane to what you're going to be doing in full stack in our curriculum. But it's interesting. You'll note that if a byte begins with 1, that means it is part of a multi-byte sequence. If a byte begins with a 0, that means it's a single byte ASCII value. So for instance, J and S both begin with zeros. They are single byte values. The smiley face emoji begins with a 1. It's part of a 4-byte value. And in fact, the number of bytes corresponds to the number of ones that we start off that value with. You'll note that the emoji starts with 1111, meaning that there are 4 bytes total that this emoji belongs to. So it's a very clever encoding scheme. It's very space efficient. It's very error proof. If we ended up accidentally with a frame shift where we are looking at, say, the second byte of that emoji, we see 1001. Immediately we know that we are in one of the multi-bytes of a multi-byte value, but it's not the start byte. It's one of the trail bytes. It's one of the ones that comes after the first byte, because all of the other bytes start as 1110 or 110 or 11110 or 0 something. So if I see 10, I know I'm somewhere in the middle of a multi-byte sequence. So UTF-8, great format, backwards compatible, forwards compatible, handles Unicode, space efficient, all the things. Then there's UTF-16. UTF-16 actually predated UTF-8 sort of. It was based off of USC2 and other things. It's got a lot of ambiguities. Depending on how you parse it. It's incompatible with ASCII. It's not as space efficient. It's basically just not as good a format. So just because it's a higher number, don't assume that you're dealing with something more powerful. In fact, UTF-8 is generally a more powerful scheme. We've figured out how to encode numbers in binary. We've seen how to assign text to numbers and encode that in binary. What about something more graphical, like an image? The way that the human eye perceives light, it's got cone cells that respond differently to different wavelengths. So if you have just red, green, and blue light, packed in closely enough, the human eye can't distinguish it, the cone cells become activated, and they get activated different results as if they were colors in between. So all we need to represent color is red, green, and blue light, and the human eye can't perceive any more complexity than that. And if we group each of these as a subpixel, a little light bulb, a little LED, and we group them each into a square, which we call a pixel, and each square gets different brightnesses for each subpixel, then we can display images. Zoom way in an LCD, and that's what you would see. So what do we need to encode the different brightnesses of these lights? Well, all we really need is numbers. A number value from 0 to 255 saying how bright that particular subpixel should be. A group of 3 of these is needed for each pixel. So we need 8 bits plus 8 bits plus 8 bits, or 24 bits, to encode a given pixel's color and brightness and luminance and all that stuff. And guess what? If we've got 8 bits making up 256 values, times 256 values for the second 8 bits, times 256 for the third 8 bits, that's 16.8 million possible combinations of numbers for 16.8 million possible combinations of RGB values, meaning 16.8 million different things that can be shown in a pixel, colors and lightnesses and brightnesses. Now, if we're only dealing with black and white, all 3 of those red, green, and blue subpixels have to be the same brightness. Otherwise, we would perceive more red than green or more blue than green or something like that. So if we hold all 3 of those together, it's really like we only have 256 possible brightnesses. So sometimes when designers need a lot of fine-grained grayscale, they use a higher bitrate monitor, not 24-bit, but something like 32-bit or 64-bit monitors. I don't know if those exist. What about sound? Ada Lovelace predicted this way back when. She said the analytical engine might act upon other things besides number, where they found whose mutual relations could be expressed in the science of operations and are susceptible to adaptations to the actions of the notation and the mechanism of the engine. So for example, pitched sounds in the science of harmony can be susceptible to such expression and adaptation. And she was predicting that way back when. Well, yes, we can encode sound. Again, everything can be encoded as numbers, and numbers can be encoded in binary. So a sound wave is just a bunch of levels of where the wave is up or down over time. Over time, it's just a sequence of values, so we just store a list of these things, and each value says where the wave is up or down at any given moment, and that's just a number. And we call this PCM, pulse code modulation. Okay, we've seen where physically the information lives and the trade-offs involved in those physical different technologies. We've seen what the information can look like and what kind of information it can hold, and that is our encoding scheme. Now we have to figure out how we use these encodings and what we can do with them. How does the CPU access them? What kind of things can we encode? What's doing it? How do we take advantage of it? So remember that a CPU is just a giant box of electrical switches. If we set the switches on the input side and run current through the system, some current will flow out through terminals on the other side. And those different terminals might show different results. Different light bulbs light up, different screens light up, different sounds are played. Whatever device we attach will become activated according to that output pattern. Keep running this over and over again, and we can get something that's very interactive. But how do we set the switches? Do we physically go into the CPU and hit a bunch of switches or put a bunch of ones and zeros in place? Well, kind of. We will write data in the format of a bunch of ones and zeros, and then we will feed that data to the CPU, and it will run it as a program, performing all those operations. Now, what does that look like? That is known as machine code. And every computer, since it's a different bundle of switches, reads different machine code depending on how it was designed. So here's example machine code. We have an instruction, something we want the processor to do. It's encoded as a bunch of on-off states for the input switches, zeros and ones. That's that instruction row. Now it'll be interpreted by this particular machine because of the way it's wired as take the value in register 1, take the value in register 2, add them together, and put the result into register number 6. This is just a totally arbitrary thing about the way that the computer was wired up, the way all of those transistors are connected. That if those on-off switches are set according to these zeros and ones, then the resulting semantic meaning of that, the logic that will be performed, will be to add a number in one register to another register and put the result in a third register. As you can see, we could write our programs using this kind of on-off state switching logic. but it's very difficult for humans to do. It's very error prone. People did it. It's how we got started. It's how we bootstrapped ourselves into running computers that did things. But it gets lame pretty quickly. So instead, people started writing assemblers. Assemblers are programs that would read in text, like add T6, T1, T2, and it would convert those textual formats directly into machine code, one-to-one correspondence. So an assembly language is a text version of these opcodes, these instructions, these machine switch states, these on-off states. Every assembly language command corresponds directly with a given sets of on-off states as a machine code instruction. But this is much easier for humans to work with. It's far easier for us to distinguish between add and sub versus 00010 and 00001 or something like that. So now we have an easier way to write programs, but it's still extremely machine-centric. It's still all about shuttling bits across the silicon, moving things in and out of these data buckets, these registers. And that's very difficult to figure out how to code whole programs that way. This is where USN Rear Admiral Grace Hopper comes in. In 1952, for the A0, she writes a compiler. A compiler is a translation program. It takes in a language of one format and it spits out an equivalent program in a different language. So instead of writing in assembly, we can write in something much more like English, much more textual, much more conceptual. And now these concepts do not map one-to-one with machine code instructions. For instance, loop 10 times is not a machine code instruction, but loop 10 times can be transformed into 10 different instructions for the machine to run. So now we can write in a conceptual way, in an Englishy way, and run a compiler program which will translate that into machine code. Or we can write in some language that gets compiled into a different language. It doesn't have to go from high-level language to low-level language. It could go from sideways, from one level language into another language of a similar level. This process of compilation is sometimes slow, so when you hear the system is compiling, it means it's translating our language in one format into a language of another format that is more useful for a given environment. And once this Pandora's box of compilers was open, we had an explosion of new languages and new programs and computers that could use them. Now, this gets a little bit more complicated. We say that we translate source code to object code, but the object code might not be machine code. It might be another language which the operating system uses, and the operating system talks to the hardware. And there are more layers where you've got a kernel of the operating system, and you've got system calls for the operating system. And the thing that I really want you to take away from this is not any specific exact understanding of these layers, but just knowledge and understanding that all of programming and all of computers are shells and layers of abstraction. At the absolute lowest level, we have physical electrons whizzing around in silicon and getting trapped in floating gates and things like that. Not abstract at all. One level up from that, we've got the idea that we've got on and off states that are being stored in memory. That's more conceptual, even though it's got a physical underpinning and implementation. One level above that, we have logic being performed with logic gates. A level above that, we've got these logical components and units like adders and full adders and cycles and clocks and things like that. One level above that, we have whole chips that are performing operations on input strings of machine code and generating output results by switching on devices. A level above that, we have conceptual languages, higher level languages that get compiled to machine code. We've got an operating system kernel, system calls, shell, libraries, applications, so on and so forth. Layers of higher abstraction where we sacrifice some of the concrete understanding in return for an easier to use system. Now this goes all the way to the point where some of our languages don't talk about memory at all. They don't talk about loading information into registers or reserving space or any of that information. The program itself analyzes what you want to do and goes and automatically figures out how much space it needs, reserves that memory, and then handles cleaning it up and releasing it back to the operating system later. So some computer languages don't have any built-in sense of memory existing, and it trusts the system to figure it out for it. Now, this is nice because from an author's perspective, we don't have to think about memory. We just write stuff. I mean, we really do, but we don't have to explicitly annotate stuff about memory. We just write what makes sense logically and then let the system deal with it. It's a downside because now we're no longer in control of that, which means maybe the system will decide to move things around in memory at an inopportune time when it would slow things down, right when we want things to be fast. So by sacrificing that and letting the system deal with it, we're just trusting that it'll kind of guess when the right time to do things is. It won't break the system. That's a nice thing about memory managed languages. We can't accidentally shoot ourselves in the foot, so to speak. But we give up the potential for maximum performance because we're trusting the system to do it when it thinks it should do it. Okay, so we've got now all these layers of abstraction. How do our programs get influenced by this? What ends up actually happening? For this, we're going to start talking about linked versus continuous data structures, and there'll be some overlap potentially with your initial lectures on these concepts of arrays and linked lists. But we're going to take a look ourselves. So here's a graphical representation of memory in the computer. Every one of these cells is full of some data. And the data can be empty or it can have some information, and it's being reserved by different programs. And we never want to overwrite data that's being used by another program. So we only ever take free memory and reserve it for ourselves. Imagine we're storing numbers that each take 3 of these cells or blocks. Maybe they're each like 3 bytes or something like that. It's a weird format, but we'll roll with it. If I wanted to store 5 numbers, there are 2 different ways I could do it. I could store them all in a row in that contiguous space in the upper left. So I store the first number in the first 3 blocks, the second number in the second 3 blocks, and so on and so forth, just right next to each other. A downside, of course, is that I need to go find enough blocks in a row so that I can actually do that. But an upside is, since they're all very close to each other, it's very likely that when I pull this from the RAM, say, into the cache, remember that we're always feeding data down from the higher level memory structures that are big and slow into the lower level ones that are small and fast. Well, since these are all right next to each other, it's very likely that they will be included in the cache, and that'll mean that it's fast to access all of them. But a downside is, yeah, I got to go find all that space. Now, what about another way of storing this information? What about a linked structure? Maybe I store the first value in that cell in the middle there where it says linked. And right next to it, I don't know where the next one is, so I'm going to have to put in a number that says which cell to go to next. Maybe I'm in cell 55, memory address 55, and I say the next number you should go look for at cell 78. So we go look at that portion of the memory, address 78, and yes, here's the next number, and then it's followed by another pointer, another address of where to go next. And I can keep bouncing around my memory like this. A big advantage here is I don't have to know how much memory to reserve ahead of time. If I want to store a 6th number, I just go find another block of 4 cells to put it in, and I wire it up. Conversely, if I want to remove a number from the middle of the list, I don't have to move everything else down. I could just remove that middle number and make sure that the address of the prior number now points to the successor of the middle number. So it's all about rewiring. It's all about labeling where to go next in the memory to find things. What about downsides? Well, one downside is it might be slower because I have to go look in different memory locations. And maybe that memory didn't get included in the cache. So I can miss the cache, so to speak. Another big downside, what if I wanted to insert something at the end of the list? The only information my program has is where the first thing is. So if it wants to find the end of the list, it's got to go to the first thing, then the next, then the next, then the next, then the next, and finally it finds the end of the list. And now I can say, write in an address of where I'm about to go next and find some free space. So ups and downs, pros and cons, things to consider, trade-offs. Trade-offs are the theme of classical computer science. The array data structure is a structure that is contiguous, this top left idea. And the idea is we will know where the array begins, how long it is, how many things are in it, and how many cells each thing takes up. With those 3 values being kept and referred to, we can jump into any point in the middle of the array in one step. Well, one constant sequence of steps. So for example, say I want to go to the 4th item in the array. How big is every item? Maybe it is a byte. So I know I want to go to the 4th byte of the array. Where does the array start? It starts at address 3A6. So I add 4 to 3A6, and I get 3AA would be where my hexadecimal ends up. And if I go to address 3AA, that'll be the 4th index. So we see this is why arrays are 0 indexed. So actually the 4th slot would be the third index, because if I add 0 to the address, that's just the start of the array, which is where the first number is. If I add 3 to the address, that is 4 slots over, because the 0th number means don't go any slots over. 3 means go 3 slots over, so that's the 4th slot. So what about JavaScript? In JavaScript, we have a bunch of built-in types. These are ingredients that the language provides. JavaScript doesn't have a specific way to say, reserve so many spaces of memory, or I want to put stuff in this address. JavaScript is a higher level language than that. It is automatically reserving memory for you and releasing that memory when it's no longer being used, what's called garbage collection. JavaScript consists of a bunch of primitive types. These are types that cannot be edited after the fact. So for instance, undefined, null, boolean, string, number, and symbol. Some of you may be saying, wait a second, I can change a number. But in fact, you really cannot change a number in JavaScript. And let me show you what I mean. If I say some string is equal to hello, I can read in a value from that string, such as the second index, which is the letter L. I can also write string at index 2 should now be F. And what we might expect if I log out string is, well, let's see, 0, 1, 2 is the first L, so should it be hello now? It's still hello. I cannot modify a string value. The only thing that I can do is I can change the variable str to point to a different string. That is not to say that the string has changed. That's to say that I've put a different string into the str variable. So strings are in fact immutable, in other words, unchangeable in JavaScript. And all of these primitives are immutable. They cannot be changed after the fact. You can only change what the variable points to. Conversely, an object, which is every other kind of thing in JavaScript, is an object. Regular expressions, date objects, typed arrays, functions, all of those are objects. They can change. And this is a difference of what we call pass by value and pass by reference. And to really understand this, you have to understand memory like we were just talking about. Here's an example. If I assign the numerical value 5 to the variable x, then the program knows that when we want to see x, we should go over to the part of our memory where we've stored a number, read in that number, and it is 5. If I say y equals x, a new variable, this is actually copied. The value is copied to a new location in memory. So now twice as much memory is being used in the program. There's a numerical 5 value taking up 64 bits somewhere in our cache or our RAM or wherever. And there's another numerical value, also standing for 5, 64 bits worth of information being stored in another location. And x and y are basically just the addresses of where to find that value. If I change x now and I say x should point to 8, then I'm going to go to wherever the 5 was stored for x, and I'm going to modify it so it now reads 8. And now I've got two separate locations in memory where numbers are stored. They both say something different. And if I console log out y, it's going to say 5. So far, so good. What about objects? Objects don't behave the same way. If I say variable x should store some object with age is 5, now x is still going to be a reference to an address where I can go find the object storing 5. And that object is going to be stored in memory somewhere. It's going to take up who knows how many bytes. Maybe it takes up 10 bytes or 4 bytes or something like that. If I now say y equals x, this is where it differs from the primitives. This is where objects behave in a very different fashion. Instead of copying that value into new memory, y will be an address that also points to the same object in memory. So if the object takes up 5 bytes and I say y equals x, I'm still only taking up 5 bytes. X and y both just hold an address of where to go in memory to find this object. Why does this matter? Because objects can be mutated in JavaScript. If I say x.age equals 8, I am going to go to the object in memory, modify it to have 8 there instead of 5, and now look what happens if I log out y. Even though I said x's age should change, y refers to the same object in memory as x, so y.age now also spits out 8. And we should not be surprised about this, understanding that when we assign a variable in JavaScript to another variable that holds an object, both variables are now just references to that same object in memory. They share references to that object. Conversely, if I reassign the y variable to point to a completely separate new object, now there are two different objects in memory. Y equals a different object doesn't convert the X object, it just changes the Y pointer to point somewhere else. So x.age still reads 8. Okay, coming up in your full stack education, you're going to be hearing about certain abstract data types and data structures like linked lists, stacks, queues, etc., that use memory in performant and clever ways in order to realize certain universal concepts. In the meantime, I hope that you enjoyed this video lesson, and we look forward to seeing you on campus. Thank you and goodbye.